the goal in this problem is to determine the speed of hockey pucks shot along the ice. There's some rod that rests on the ice. Okay, so there's some fixed point that it rotates about. All right, so it would have some radius, and this thing's going to swing, you know, and whack a hockey puck and get it going somewhere. That's a stickman picture. Or I take that back. We're catching it. We're not whacking it. Thinking of a different problem. So let me amend my thing here. So there's a basket that catches, and some object's going to come in here with a speed, make this thing move around. So slides perpendicular to rod's caught in the basket, then the rod rotates. And if we know the length of the rod, the mass of the rod, the mass of the puck, and then it says the frequency of rotation of the rod and the puck. Well, that's just angular speed. So if you wanted to, you could underline the words on your handout that says frequency of the rotation. That's just angular speed, right? Because it's some number of radians per second. They believe you can determine the speed across the system here. So you might recall, if there's a collision, the first thing to do is to go through conservation of momentum. Just get that in your head. Conservation of momentum. Our entire context for momentum and its conservation has been about collisions. Okay? And so if something collides, conserve momentum, that's inevitably going to give you the speed that would then be useful in an energy calculation. Right? So conservation of momentum, it's angular momentum because I get something spinning. So I set up my momentum balance, if you will, for angular terms. And just like we've seen previously, the initial side has to equal the final side. So I use the sub-zero for initial and no subscript for final. The initial angular, or the moment of inertia initially, will be related to the puck, and omega equals V over R. All right. So I'm going to leave omega on the right-hand side because we're wanting to pitch this in terms of the angular speed that we obtain. So remember, what we're aiming at is a function for speed, linear speed, that's in terms of the masses, the length of the rod, and the angular frequency or angular speed of the rod. So we want to leave that final angular speed as angular speed. We're not going to discombobulate it. If you did, and we did that in other problems, okay? So you don't want to just be stuck in the pattern of I did this the last time. You want to pay attention to what is it that you're being asked. So we have this right here. So the initial rotational inertia is associated with something that's not rotating, the puck. And the puck is just a little disk. And little disks are like little point particles, and they're just an mr squared. That's what the initial rotational inertia is. And of course, one of those radiuses kills one of those things. And you get mr v naught just equals I omega. Now the I that's with the omega is going to be the combo of the rod, which has its own moment of inertia. That's not going to be an mr squared. It'll be mr squared-ish. All right? And then the puck because it's caught in the basket, will become part of the rotating system. So the rotational inertia on the right-hand side, we can just leave alone for now, but we have what we need. In fact, we don't really need more than this. We can just get the speed from conservation of momentum, which is why these are angular momentum problems. Okay, we're not going to always deal with the energy. So V naught would just equal our I omega over mr. So how could we, in fact, I'm going to kind of rearrange this a little bit for our focus. Now we're going to bust out this I for this combined system. So I'm going to come over here to the left, and so the I of the, I guess, rod puck system is going to consist of the puck, which is mr squared, plus, if you look in the table for a long, thin rod, which is what we're dealing with, that rotates about one of its ends. So again, you'll be looking in your book for a similar problem if you get one like this. And you would find that ml squared over 3. So this is going to be the combined rotational inertia that's on our right-hand side here, is all of this. So V naught would equal a bunch of stuff over mr times omega, and that bunch of stuff is going to be mr squared plus ml squared over 3. And I'm using m as the mass of the rod. Big M is the mass of the rod. I don't know which one weighs more, probably the rod than the puck. And so there are some simplifications that we can obtain in this mess. So V naught, if I just multiply, get a common denominator of 3, all right, I can write 3 mr squared plus ml squared over 3 over mr. Kind of cramming things together there. Sorry about that. Let me sort of separate things here. So what this will bust down to, when you go through all this rigmarole in the math, is V naught will equal 1 plus mass of the rod over 3 times the mass of the puck times the length of the rod, angular speed. So this is our V naught, simplifies down to that. And that's all we had to do, was come up with an equation that related the mass of the system, the component masses of the system, the length of the rod, and this angular speed that rod has. So if we measure the angular speed, so we'd have some photo radar that measures angular speed. Okay, now you're thinking, okay, why not just get a speed detector for the puck? That'd be another way to go, all right? But maybe those aren't as reliable. Maybe they're too expensive. Maybe we have a simpler way, an angular speed being the only variable and everything else being constant, you can more quickly and reliably detect that. So those constraints are external to the physics. They constrain what we do in the physics. You know, why? Is there a better way to do it? Maybe. Okay, the solution that works in this context doesn't work as well or at all in the other context. So, but again, it's just a physics problem, and we can use these things to figure it out. All right. Next problem. You are a member of a group designing an air filtration system for allergy sufferers, and you want to measure the mass of pollen in an air filter where it's used, and in order to do that, little rectangular box, little hole in one side, and once pollen goes inside this box, it picks up an electric charge, which is not hard to do. We'll learn about that in next semester. And it's accelerated by an electric force that's in that box, all right, to some speed, the speed of 1.4 meters per second. And why would we want to do this? We want to have something, as many things as possible that are constant. All right? And this little pollen particle is going to run into something and make it swing. So if we look at the design here, the design is that there are really tiny uniform length bars that are able to pivot. So if something hits them, it's going to make it move. All right? If you read down in the bottom there, we only need it to move an angle of 10 degrees, which is not much. So literally, all we need is for that pollen particle to hit the bar and just kind of knock it just a tiny bit. And if I get that angular displacement on the bar, then I can figure out, is this a pollen particle? I can detect that pollen particle, all right? So, and then it releases it. So if it's pollen, it catches it and drops it. If it's not, something else happens. So there's all of this stuff in the bottom. So it tells you that typical pollen particle is 4 nanograms. The bar is basically 70 milligrams. So 70 1,000ths of a gram. So it's a tiny bar. So we're expecting a really tiny little metal thing. You probably have a hard time, you need a magnifying glass to really see it. But guess what? The pollen particles are really, really tiny. So this is unsurprising. And with a moment of inertia that for some reason is 1/12 as much as if all of its mass were concentrated at its end. All right? So what is that going to tell us to do? All right, so first thing, we're going to conserve momentum. And we always conserve momentum because it's a collision. So our usual here of the initial angular momentum equals final angular momentum, which means I can write I omega initials equal I omega final. So now let's get at what we have here. So initially, we just have, over here on our initial rotational inertia, we have the mass of the pollen particle at a distance L, it's hitting the end of the rod, that is L long, ml squared, times that initial angular momentum, and that's going to equal the rotational inertia of the pollen particle that is stuck to the bar. So it's important that you catch what I was saying as I was writing it. All right? So I'm going to switch to a highlight mode, and address this thing here. So in the final state, the moment of inertia consists of the pollen particle that gets stuck, plus sign, to the rod. And that's the mathlish interpretation of that. Those masses come together. If the pollen sticks to it, or which it will because of the charge, then now I have an ml squared, or a 1/12 ml squared for this rod, plus an ml squared for the thing stuck at its end, at length L. That's what's going on in the problem. And then this has that final angular speed. So, it's hard to remember because I just said it, but I've been saying these things over and over again. If you listen to the video later, there's a thinking that goes with this. And now you can just plug and chug equations. That's another way to go. You definitely need to know that I omega is going to be some sort of mass times a length squared, a radius squared, maybe some fraction of that. It's always the same sort of structure, all right? So now we've converted, we have all the mass, length, angular speed terms. We can start changing things up. So omega, remember, V equals omega R, or in our case, V equals omega L. So that means omega is going to be L over R. I'm sorry, that's not right. Omega is going to be V over L. Gotta keep that straight. So I'll have ML squared, and if instead of omega I put V over L, I'll have V naught over L. Same thing over here. I'm going to separate the masses. I'm going to factor them out. And I'm going to have L squared, because they were common to both terms, and a V over L. And I think you see how not only do these denominator L's kill one of the squared L's, but common factor on both sides just drops out. I don't need to go through every algebraic step. I can just kind of cancel things that are cancelable in place here. And so I get an M V naught equals and right here I want to kind of give pause to the fact that look at what the conservation of angular momentum gave us. It gave us what we'd expect if just two things ran to each other along one dimension. Little mass at some speed runs into some other mass. They combine if they stick together, which they do in this case, and they have a new speed. It's just conservation of linear momentum. Fell out of the tree called angular momentum. All right? We could, if it's a collision of this type, how many times in a row? This is like the third time or something, where we just keep shaking linear momentum out of the angular momentum tree. If we're sure of the constraints of the problem, we could probably just go straight to this. It seems to always work out that way. That means that sooner or later it won't. So you always want to go through the motions to make sure that you're right. And so what we would get is we do know initial speed. We're given that in the problem. So that means our final speed is going to be m over this weird sum of masses times the initial speed. And so our final speed, if you plug and chug all those numbers, you'll get 9.6 times 10 to the minus 5th meters per second. I'll spare us the writing of all of that stuff. Now we need to conserve energy. So it is the case that our rotational kinetic energy needs to equal our gravitational potential energy. And that means, again, rotational kinetic energy is 1/2 I omega squared Gravitational potential energy is 1/2 mgh. Now, h is going to be an interesting thing to calculate because we're dealing with a rod, okay, of some length, okay, going through some angle. Well, this is our height that we're talking about. Or that would be the height in the energy formula. Right? So the little pink triangle is just that lever arm swinging up some degrees, which we know to be 10, the way the problem is structured. And so what I have here is this this triangle right here. All right? That side, that reduced side of that triangle, is the length of that rod minus the height, but the hypotenuse of that triangle is still the length of the rod. So the cosine of theta, which I know theta is going to be 10, the way the problem is structured, I can now write an equation for h that's in terms of the length of the rod and the angle the rod swings. Because I don't know h. That's not given. Only thing that's given in the problem is that the length of these little rods is something, and the angle that they need to swing through, if it's a pollen thing, is 10 degrees. So I have to rewrite this. So this basically gives me cosine of theta will be L minus H over L. And what that boils down to is my H is going to end up being L times 1 minus cosine theta. That's going to be really helpful. All right, to have that instead of H, which I don't know. I have to put it in things that are known or expected in my situation. So we could, in our next step, 1/2 I omega squared will equal mg L 1 minus cosine theta. So the plan, if we go back to the problem statement, your plan calls for a bar that weighs so many grams. Is this going to work? If the bar weighs that many grams, will it work? And one thing to do is, do I get a reasonable length for this mass bar? Can I even fabricate a bar of whatever length this is given all these constraints? So I'm going to have to add a screen here to finish the deal. So what's going to happen is we are going to get 1 plus m over 12m times v squared equals 2gl 1 minus cosine theta. That's just taking the equation to the next step, which means if I solve for L, I have all that stuff surrounding L, so put L by itself. The numerator is going to be what I have on the left-hand side here. All right. And then I'm going to have this 2 1 minus cosine theta. I'm going to change things up here a little bit because I'm going to separate all of that because that stuff's a bunch of numbers, and I'm going to have v squared over g. So I have all of this stuff. That is a pure number, and the reason it's a pure number is that the m over 12m reduces to no mass. It's just going to turn out to be a number. Cosine of theta, 2, 1, all those things are just numbers. So this is just some complicated fraction of the v squared per g. And v squared is meters squared per second squared. G is meters per second squared. Therefore, you get meters. So it's, all of that stuff ends up being the fraction of the length, but it's or the fraction of this interesting combination between speed squared and acceleration. So if we plug and chug a few things here, so let's take a swing at that. 1 plus 7 times 10 to the minus 4. I'm going to leave it in grams because I'm just canceling them out. You could bother to change everything to kilograms, but it wouldn't help you in the problem at all. 2 times 1 minus cosine of 10, that was given in the problem. I think I made my bar a little too long. And then I have my v squared over g, so I have the 9.6 times 10 to the minus 5 that we calculated earlier. We'll use 9.8 for g, and I get a length. Your calculator will spit out something like this, which is just 0.451 millimeters, or roughly half of a millimeter. Now, if you had a ruler in front of you right now, you can see half a millimeter with your eyeball, right? So that means, yeah, you know, if I could take a paper clip and snip off the end and have it fall somewhere be less than a millimeter, which you could do right now if you had a pair of snips. That means somebody can make this sort of rod. This is an incredibly tiny rod, and what it's pivoting on, God only knows. All right? So I guess here's the thing. I wouldn't be surprised to find that this sort of rod can be fabricated. Now, either it can or it can't. So, but all we did here was, well, if the rod has that mass, okay, this is how long it's going to be under the rest of the constraints in the problem. That's really what we did here. So the practical application of this, which won't matter to many of you in a life sciences physics class, but it would matter to those in a engineering science major, hard science major class. The way the problem was stated in real life, that's the set of constraints that the engineering firm is given at hire. And they go off and figure out how to do it or if it can be done. Every one of the sciences, whether it's engineering, physics, biology, chemistry, you name it, medicine, there's always a set of constraints that determine what you can and cannot do. And the thinking is identical whether or not it involves this set of equations or some other set of equations. Okay? So the main reason that, say, people in a life sciences college physics course do all this stuff, they want the background knowledge, but they want the thinking more than they want the background knowledge. Do you have this process? Have you experienced this at all? For the engineers and whatnot, they definitely have to be able to also do it this way in particular, or at least be familiar enough. All right, so either I can make 0.5 millimeter long sticks, or I can't. If I can, this works. If I can't, go back to the drawing board. That's assuming we did the math right. All right, the next one. Design a new stunt for the opening of an ice show. A small 50-kilogram skater glides down a ramp and along a short level stretch of ice. Gliding along that level, she makes herself as small as possible. I guess she crouches down or something like that. And then grabs the bottom end of a large 180 kilogram vertical rod. 180 kilogram. That's like twice my weight, twice my mass. Okay? That's like 2 people. She grabs the foot of the bottom physics professor who's holding onto the feet of another physics professor. All right. Turned vertically through an axis about its center. The plan is for her to hold on to the 20-foot long rod. So this is making sense. I can believe a rod being that heavy. And it has a uniform mass distribution. What's the minimum height of the ramp? All right. Now, this last thing, doing a quick integral tells you the moment of inertia rod about its center is 1/3 of its moment of inertia, as if all of its mass were concentrated at the ends. That means 1/3 of mr squared. That's what that means. If all the mass is concentrated at the end of a radius, that's an mr squared. All right? So, we're just going to go, this one, we go straight into, I'm going to conserve energy first on this one, just because it's simple. The gravitational potential is going to have to equal that initial kinetic energy when she grabs the bar. So mgh equals 1/2 mv squared, v naught squared. And we've already seen this. This means that my initial speed has to be root 2gh. We almost didn't need to do this. So this would be a basic idea. If it's just exchange of gravitational potential to speed, that speed always is the square root of 2gh, the height that you fall from, so to speak, even if the path is in the way of your falling. All right? Since it's on ice, we get to pretend there's no friction. All right? Now we can conserve momentum, which is a longer spiel. The reason I did that is so we can put this, the exchange of energy preceded the momentum. All right? In the other ones, the momentum led to an energy exchange. Now the energy exchange leads to a momentum. So I can do it in reverse order. So if you can map out a problem, what's happening first, what's happening next, and it tells you that's the order that you go in your computations. Again, the I omegas. So let's do this right-hand side. So initially, the skater, mr squared, v naught per r. I'm not going to explain that again. Done that a few times in a row. And then the skater brings her mr squared into 1/3 of the mr squared of the rod, and together they obtain a new angular speed, which I'll write as v over r instead of omega. Same idea. The skater collides with the rod and they become one complicated mass system. Not really that complicated, just a sum of 2 things we'd get from a table. And this boils down to, as we've seen over and over again, a linear momentum of the thing that was moving is equal to the total inertia of the thing that gets moving because they run into each other. And so this leads us to, and I'm going to conserve space as well as energy and momentum, my v, this final speed, will be an m, well, and that, remember what v was, it was root 2gh, or v naught was root 2gh. Oh, I need to erase things here. I gotta get my fractions right. Looking at the wrong. So if I solve for v, I'll get m over that fraction, or that weird mass compilation, times my initial speed, which is what's up here at the top. Okay, so those gotta come together. So my final speed, here's where can get a little interesting. So in white, I did the energy exchange that led to the speed in the momentum exchange. And now that momentum exchange is going to translate into swinging the bar up above ground so that this mass system of bar and skater go up in the air, thus doing what? Increasing gravitational potential energy of that new system. So we go from energy exchange to momentum exchange to another energy exchange. So mapping out the problem tells you what is going to be the analytical approach to this, all right? So we have our new speed equation in terms of mass and height, yay. So now, I'll need to clear some space here. Now that speed will cause a rotation of that combined skater rod mass, and then there will be an increase in gravitational potential. So I'm going to have 1/2 I omega squared equals an mgh, all right? So 1/2 of that little mass plus 1/3 of a bigger mass, v squared. Now, all I did was the r's drop out. Okay, so this is the same stuff as before. And my height, the idea is that this skater, there'll be a vertical rod. She grabs that rod at some high speed and it swings her up so that she goes all the way to the top. Basically going through 180 degrees. So that means that her new height is going to be 2r, double the radius, because she's going to swing all the way up, all right? So h becomes 2r in this problem. So just look back at the, and it swings her to the top. So if something's going to swing to the top, that's 2r. So now we can get at our problem here. So if we want to figure out the speed that she's going to hit this thing at. So remembering that our speed was this weird mass fraction bit, square root of 2gh, all right? So that means this thing here is getting squared. Okay. Yay, team. That's going to be fun for the whole family. So what is that going to look like? Well, if I square the square rooted part, I just get a 2GH. Okay? So that'll be nice. But then this other thing, this weird mass squared business, I'm going to have 1/2 m plus m over 3, and then there's going to be an m over m plus m over 3, that whole business squared, times 2GH will equal 2mgr. Now, hopefully you see that this mass sum is going to wipe out one of these that's getting squared. All right? So this will boil down to a, well, notice, I guess first this half wipes out that 2. So I'll get GH little m squared over little m plus m over 3. Be careful with the little and the big m's. This thing here is a little m, but it sort of looked like a big M. Equals 2m gr. That means my h, we just kind of cut to the chase, 3m plus m over 3m times 2r. And all of this boils down to h is going to be 2 plus, I'm skipping some work, and if I plug and chug all of this, the height that she goes to is 13.4 meters. So that means the rod length would be half of that. So this is a 6.5 meter, 7 meter rod, somewhere in there. That's a large rod, okay? 6 yards would be 18 feet. We were told that the rod was 20 feet long, okay? So if this is the case, now I can compute my initial speed with that square root of 2GH business, and that means my initial speed, if I plug all of that stuff in, is 16 meters per second, which is roughly 35 miles per hour. I don't know. Can a skater get up to 35 miles an hour? Sure. I'm not sure that I want to try to grab a pivoting rod at 35 miles an hour. So if I were the skater, I would want to know, okay, how am I going to do this without breaking my arm? You know, or pass, you know, this seems to, maybe we need to rethink the design here. Okay, so if there's a way for the skater to collide with the rod at 35 miles an hour to grab a hold of it and start swinging. So if it's maybe there's just some sort of rope to catch or something like that, but if it's actually grabbed the rod at 35 miles an hour, I'm thinking this won't work well. That's my guess. Okay, so sometimes it works out, and sometimes the math says this ain't gonna work. Go back to the drawing board. This would apply to any area of science, not just physics. Last problem. Hired by a company, designing a new water slide. Design has a customer going down a curved slide, moving horizontally at the bottom. At the end of the slide, customer grabs the end of a 16-meter long vertical bar. This again. All right, hope this works out. After grabbing the bar, the customer swings out over the pool of water, and when the bar swings out to its maximum distance, customer can drop off and fall straight down into the water. So sounds like this is going to be just going a quarter turn, just going up some height. Bar has 5 times the mass of the 60-kilogram person. From an engineering handbook, you find out moment inertia is this 1/12 business again. So energy conservation says gravitational potential equals the initial kinetic when we meet up at the bar. And I'm just going to skip. We know the initial speed would have to be 2gh. Every time it's just a simple exchange of potential, gravitational potential to kinetic, it's just, we know the speed business. The masses are become irrelevant, and it's just the height and speed in that relationship. So we'll spare all that extra work. So momentum, L naught equals L, which means my I omegas are in balance. And so now we can start plugging and chugging. So I have, again, treating a person like a point particle. They are an mr squared. Their angular speed would be the linear speed over the radius that they're inevitably going to get going on. And again, what do we have? We have another sum of course, my final omega is V over R. I'm going to have the person's rotational inertia plus, this is incorporating all of the constraints given in the problem. The mass is 5 times m, so that the 5m is accounting for the bar being 5 times the mass of the person. The 1/12 L squared is exactly what we found in the handbook according to the problem statement. All right. So once again, these things, now the L is going to be equal to R. All right, so I can change this to L. And once again, I think what I'll do is just change these L's to R's, since that's what they are. And you get an mr squared, I'm sorry, you get an mr V naught equals another mr out in front of, I'll put mr squared out in front, and you just get a 1 plus 5/12 here. V over R, and of course that R kills one of those. So mr V naught equals so MRs drop and your initial speed is going to be 17/12 your final speed. which is supposed to equal root 2gh. So that means your final speed would be equal to 12/17 root 2gh. So again, an energy exchange leads to a momentum exchange, which allows us to determine what the speed would be after that momentum exchange. And now we can go back to an energy exchange. And it's again, now I have rotational kinetic energy because this bar is swinging. So we have again, so here's this rod, mass gets added, makes it swing up, and then the person drops. So rotational kinetic goes to gravitational potential, which is another half I omega squared equaling an mgh. So I have 1/2 of, let's see, what was it? It was, if we go back up to the top here, that thing right there is that rotational inertia. And so plugging and chugging all those values in would give us some value, and so that would be the ends up being the 12/17 mr squared v squared over r squared, and that's going to equal mgh. Again, r squareds drop out, and we get m's drop out, and let's take things over to the left here, and so h would end up being 12/34 v squared over g. All right, so we would compute that out and get some number for the height. I had to change my notes, so I didn't compute it, but it's a number crunch at this point. There's nothing profound to finish this with. So those are the 4 problems for demonstration purpose.